section with the continuation of my presentation on
Thank you. Okay, so thank you. Okay, so let's continue our discussion about ungauge supergravities versus gauge supergravities. The main motivation why we should be interested in studying the gauging procedure. Remember the scheme I sketched out, I partially sketched out yesterday. If we start from d=11 superstring theory, or better, supergravity, because we are interested in the low energy description of these theories. Okay, so we can start from the supergravity description in 10 dimensions of these superstring theories. For instance, type 2A or type 2B supergravity. Okay, or d=11 supergravity, which describes the low energy limit of the so-called theory. Okay, and we compactify, as we discussed yesterday, on an internal compact manifold, which is Ricci flat in the absence of fluxes. What we end up with in d dimensions is an ungauged supergravity. Okay, in a supergravity in which there are no minimal couplings of vacuum fields to any other field. We also pointed out the pros and the cons related to these ungauged theories, in particular that they exhibit interesting global symmetry structure defined by a global symmetry group G. Okay, if you compactify these theories on tori, particular that d=11 supergravity on a torus, okay, of 5 dimension, what you end up with is a maximal ungauged supergravity in which this group G, in a particular version, and we will of the theory, in which all form fields are dualized into lower rank fields. Okay, but this group G is an exceptional leap. Okay, so this group G is particularly interesting. Okay, it's an exceptional leap. Okay, so this group G is particularly interesting. Okay, and can be very large, quite large. Now, on the other hand, we've seen yesterday, we have pointed out that these theories are physically uninteresting. So they are mathematically appealing, but physically uninteresting for the reasons we mentioned. However, if we compactify the same theories on an internal manifold, which is non-Ricci flat, so it's curved, okay, with fluxes. By fluxes, I mean vacuum expectation values of field strengths across cycles of the internal manifold. Well, we end up with a theory which is in dimensions, which is a dimensional gauged supergravity. Why? Well, because the fluxes and the structure of internal manifold, induce in the low energy description and minimal couplings of the vector field to other fields. Now, minimal couplings, for consistency of the theory, have to be associated with an internal symmetry, a gauge symmetry. Okay? Otherwise, longitudinal modes would not be coupled. Otherwise, longitudinal modes would not be coupled of the vector field. Right? So there is an internal gauge group. The structure of this gauge group, okay, depends on the geometric structure of this internal manifold. You have a sphere, if you have a twisted torus, if you have a group manifold, and other fluxes across cycles of the internal manifold. Okay? So G depends on all these things which describe your compactification. In what sense does this theory describe the low energy limit of this compactification? Well, here we have to be careful because the issue is subtle. What happens is that a suitable subset of the low-lying modes of superstring theory or d=11 supergravity on this background, okay, are captured by a theory like this. A suitable subset which defines a consistent truncation. Consistent truncation means that all solutions to this model are solutions also of the higher dimensional one. Can be uplifted. Okay, this is the idea. Okay, so these theories are physically interesting. From a phenomenological point of view, they are interesting because of these fluxes and the structure of the manifold induce masses and therefore spontaneous supersymmetry breaking in general. Okay, this is something that from a phenomenological point of view we want to have. It will also induce a scalar potential. Scalar potential is the degeneracy that we have here among the scalaries, okay, and selects vacua with certain properties. Here you can have cosmological constant. So you can have ADS vacua, which are of particular interest in ADS-CFT. ADS vacua preserving, for instance, a certain amount of supersymmetry, or no supersymmetry at all. There are. So there is a number of interesting features that all these theories share. Okay. Another interesting feature is that although these lower dimensional theory describe only a subset of the low-lying modes, string theory and mapping theory on these backgrounds, they capture the full nonlinear interaction between these modes. This nonlinear interaction would be very highly would be very difficult to derive directly from superstring theory or from 11th dimension. Would be very, very difficult. Okay?
So in America, we don't need consistent truncation, right?
We do need here also consistent truncation. In both cases, we need consistent truncation. So in both cases, we're talking about supergravity, lower dimensional theories which describe consistent truncations. Remember the compactification on the topos. Okay, there the consistent truncation amounted to restricting to the zero Fourier modes in the expansion of the fields. In the Fourier expansion of the fields in the coordinates of the internal topos. Okay, and that is a consistent truncation. Okay, for more general rigid flat manifolds, you can define consistent truncations in a similar way. Okay, here the issue of consistent truncation is more subtle.
So when is that dimensional reading and when you compare?
What's the difference? Well, in both cases, you're dimensionally reducing somehow, right? But so you are defining a lower dimensional theory describing a subsector of your higher dimensional one, a subsector of modes or fluctuations of the higher dimensional one. Okay, and so in both cases, you're defining a consistent truncation, which is an effective, which is described by an effective lower dimensional theory in both cases. However, in these cases, the internal structure of the geometric structure of the internal manifold makes the consistent truncation, defining the consistent truncation more difficult because there are non-trivial interactions between the various modes. So it could be that you truncate, some modes out, okay, but the remaining modes that you retain act as sources for, due to these interactions, for those modes that you have selected out, that you have set to zero. And in this case, the truncation is not consistent. So defining consistent truncations is a very subtle thing. One way is to use, for instance, the Church-Schwarz reductions. That is to write down the 10 or 11 dimensional fields in a way that their dependence on the internal coordinates gets factorized in a suitable way. If you get that, then what you end up with is a consistent truncation. Okay, so Church-Schwarz, they give you consistent truncations. Now, within maximal supergravities, there is a general framework which is very useful for defining consistent rotations. That is exceptional field theory. There you can define some generalized Schwartz ansatz, okay? And that allows you to embed lower dimensional, certain lower dimensional gauge supergravity within M theory or maximal type okay. Okay, so these are the good features of these models, okay, which make them interesting from a physical point of view. Unfortunately, however, in these theories, G is broken. It's broken by the minimal couplings involved in the gauging. Okay. So the whole symmetry, which was manifest in these theories, is broken. It's broken by the presence of these fluxes and the structure, the internal structure of the manifold. The manifold, the structure of the internal manifold. Okay.
Prof, was the global symmetry you're referencing the same one that reflected the various dualities in the
precisely, and that's the problem. You see, because this G contained a good part of the non-string or M theory dualities. Now, if this is broken, somehow you're losing your track. You're losing track of these dualities in the presence of fluxes. Okay, and this is something you don't want. Okay, because then you're kind of losing an important information that different backgrounds are in fact different descriptions of the same physics, so they are equivalent. You're losing this equivalence. Okay, as I will show, there is a formulation of gauge supergravity in which, at least formally, G is restored. Okay, and this is the embedding tensor formulation of gauge supergravity. So this is the main advantage of working with the embedding tensor formulation. So we have these two different classes of theories, okay, in D dimensions. We shall focus on D for 4, but I will also touch upon the main features of higher dimensional supergravities. Now we can go directly in D dimensions from one theory to the other, okay, through the gauging procedure. That is, we can obtain the gauge supergravity that originate from these non-trivial dimensional reductions or compactifications, if you want. Okay, we can retrieve, we can construct this supergravity from corresponding ungauged models with the same amount of supersymmetry and the same amount, same field content. Okay, amount of supersymmetry, same field content, and we can go from one to the other through the gauging procedure. Yes.
Do this gauge theories contain anomalies? And if they do, is there a way of bringing the ungauged to the gauged?
This is a good question. We shall focus on extended supergravity. Now, in extended supergravity, you don't have anomalies. Sorry. The question was about anomalies. Do these gauge supergravities have anomalies? Now, I will focus on extended supergravity. Consider extended supergravities in 4 dimensions. Now, they are non-chiral, so you don't have anomalies there. Okay, but you can play the same game in n equal 1. So you can there in n equal 1 you have more freedom, but you can play the same game. Okay, you can introduce a duality structure and perform the gauging. There you have an anomaly. There you have an anomaly. Particular component of the embedding tensor, as we will show. Okay? But we shall focus on extended supergravity, so we won't be dealing with it. Okay. Good. So starting from an ungauged model in D dimensions with the same amount of supersymmetry and the same field content, okay, we can construct a gauged supergravity model of this kind through the gauging procedure. And in fact, when considering extended supergravities, the only way of introducing masses or a scalar potential is through the gauging procedure, without manifestly breaking supersymmetry at the level of the Lagrangian. Is through the gauging. What do we mean by gauging procedure? We mean that a suitable subgroup of the global symmetry group of the corresponding ungauged theory is promoted from global to local. Okay? And the procedure also guarantees that supersymmetry, the amount of supersymmetry, of shell supersymmetry, is restored at the end. Okay? And this requires introduction of mass terms, Yukawa terms, okay, for the fermion fields, and a non-trivial scalar potential. This scalar potential is directly related to the choice of the gauge. Okay? So you can go from here to here directly as a shortcut in the dimension. And all gauge supergravities can be obtained in this way, without having to derive them from a dimensional reduction and a truncation in some way. Okay? Obtained in this way, the gauging procedure, but they cannot be uplifted to 10 or 11 dimensions. Okay? No. Okay? So this is a normal problem. Now, it is useful to encode, and it turns out that one can encode the choice of the gauge group inside the G, the global symmetry group, in an object, a constant object, which finds this embedding. This is a constant object which encodes all these features, fluxes, and the geometric properties of the internal manifold, okay, and which is formally G covariant. If you can formulate this procedure, the gauging procedure, in terms of this object. All these quantities, masses, scalar potential, are all defined in terms of these objects. Scalar potential are all defined in terms of these objects, which is the embedding tensor. As we said before, the advantage of this formulation is that now all these modifications that you do on which are implied by the gauging procedure are all encoded in terms of this quantity, okay, which is formally G covariant. And so this means that you can describe the equations of motion. The equations of motion, which here are schematically denoted by E, generically denoted by E, as functions of the fields of the theory and of this embedding tensor, in a way that is formally G covariant, because these are G covariant. The fields are G covariant because these are G covariant. The fields are G covariant because these are the same fields that we had in the ungauged theory, which was G covariant. Then we have this gauging, that all the changes implied by the gauges are all encoded in theta and can all be written in a G covariant, formally G covariant way in terms of this theta. Okay? So that for any G in G, this is equivalent to G, and writing this in a very schematic way. The equations of motion are formally invariant under the global symmetry group G, provided that together with the fields, we transform the embedding tensor as well. And we know how to do it because the embedding tensor belongs to a particular representation of G. So we know how to do that. Because the embedding tensor is a tensor formally. So we are transforming formally. So we are transforming both. We are transforming both the fields in the embedding tensor. Remember, the embedding tensor contains coupling constants, contains masses. So it's a non-dynamical object. Okay? So what you're doing here, you're transforming together with the dynamical fields, also a non-dynamical object. So this correspondence, okay, is not a global symmetry of a single theory, because different embedding tensors find different theories. But rather, it is an equivalence between different theories. One described by theta, and the other described by g times theta. Okay, so it's a proper duality, an equivalence between different theories. So you see, using this approach, we can recover, we can systematically study the effect of the known string dualities and theory dualities on these non-trivial backgrounds by simply studying their effect on the embedding tensor. As an example, we can consider type 2 decompactification and type 2 on a torus in the presence of an H flux. H flux is the flux of the field strength of the Calvert-Ramon field, which is called H. It's a three-form. Okay? One can consider a toroidal compactification in which you give a BEV to the field strength of the Calvert-Ramon field. You're giving a BEV, a vacuum expectation value, to the field strength, which is a three-form of this two-form, okay, across a cycle of internal torus. This is a flux. What you end up with in lower dimensions is a gauge supergravity. There's specific gauging defined by this flux. This flux defines a component of theta. Now, if you apply some of these transformations, that is dualities, okay, in particular, those which are called T-dualities, okay, which lie in here, then this you see that this H flux becomes a systematic way, using this formulation, the effect of dualities, some of them are inside G, on flux compactifications. Okay? And this is a great advantage. All the non-geometric fluxes, they just arise from this kind of action on theta. Okay? On theta defining a geometric compactification. Okay? Other questions?
So why theta is non-dimensional?
Oh, because simply theta encodes vectors, that is background quantities, constant background quantities characterizing our 10-dimensional solution. So it encodes vacuum expectation values of field strengths across cycles of internal manifold. This is not dynamic; these are vectors. Okay. You can think of theta, for instance, as being a magnetic flux. You know, if you take a magnetic flux, you know, if you switch on a magnetic flux in your laboratory, okay, this is a non-dynamical thing because it's something that you that belongs to the environment. Okay, it breaks your rotation symmetry, SO3 symmetry, in space. Okay, however, if you rotate also the magnetic flux formally, your equation of motion of a particle inside it remain invariant, provided you rotate also the magnetic flux. So this is a schematic way, a very simplistic way of seeing this. Okay? Magnetic flux is something non-dynamical that belongs to the environment. You fix it. Okay, and formally, you write the equations in the cake, and formally, you write the equations in the presence of this magnetic flux, but formally, everything is still SO3 invariant, provided you rotate your magnetic flux as well. Okay. Okay. Are there other questions? So let us start describing the action of the global symmetry group G on an engaged supergravity. Let's see how it acts. Let me start from a generic D-dimensional theory. Then I will focus on 4 dimensions. Okay. So D-dimensions, we have a scalar, a bosonic sector and a fermionic sector. They are related by supersymmetry. Okay. So we are considering a theory with a certain amount of supersymmetry. We are focusing on extended supergravities, meaning that the generic supersymmetry parameters depends on a number of independent functions, which is greater or equal than 8. So extended. In 4 dimensions, this means n greater or equal than 2, because each supersymmetry generator contains 4 supercharges. So it means n greater or equal than 2. But this is a dimension-independent way of supersymmetries. So we have a bosonic sector, which contains the matrix. Then it contains the scalar fields, S running from 1 to an S, okay? In general, they contain these fields. And besides the scalar fields, it will contain in general P-forms, P-form fields, namely rank P, anti-symmetric, okay, with various P's. With the P for 1, we have a vector. Okay, they come in a certain number. Okay, so M running from a number of P forms, which I call NP. Okay. Then we have the fermionic sector, which contains the gravitinons and other firsts. Okay. In this first part, I will focus only on the bosonic sector, not because the fermionic sector is unimportant. That's not true, because all the structures I will describe, the global symmetry structure I will describe, follows from supersymmetry. And therefore, the bosonic sector and the fermionic sector are equally important in this game. Okay? Just because in the fermionic sector, the action of the global symmetry is manifest. Okay? It's more evident. Then I will also show how the global symmetry acts on the Fermions.
So the forms, you counting this up to V or up to?
Oh, okay. Yeah. So
Are you counting
mu?
Okay.
So
So counting dual forms, conjugal forms separately.
yeah.
Quotient.
For the time being, I'm just considering these forms. Okay, just now I will discuss the issue of duality. Okay, but for the time being, let us just write these fields like this. With P, well, we can have different P forms. That is antisymmetric tensors of different ranks in the supergraph. Okay, as we shall see, we can. There are equivalent versions of a single engaged supergravity in dimensions. Okay, and these are related by the Hodge duality. Okay, dualization of these forms. Okay, now I'm coming to that.
Just a reminder, when you have a zero form, that's the
That's a scalar.
Yeah, but is it a scalar or is it a scalar, like should I put them separate or?
No, they are inside. They are counted as scalars.
Okay, so mu does not need to be zero. Oh, sorry.
No. Mu is a space-time index.
Yeah. Yeah, so my question was how many components are allowed there? They go up.
How many p?
Yeah.
Oh, okay, sorry.
You allow zero components or-
Greater or equal than 1, sorry, yeah.
And less than equal to D, I guess.
There is a normal natural bound, upper bound. You cannot have an asymmetric tensor of rank greater than D. That's the most you can have. So yeah, P is greater or equal than 1. Zero forms are counted as scalars, particular scalars which are called axons. Okay, but they are counted as scalars. So they are described within the scalar sector. Okay. These P forms, well, these P, rank P tensors, they are also described as forms, exterior forms, with a basis of this type, okay? So they can be described also as P forms, and in this case, well, this is a way of describing them, which is manifest invariant with moments. Okay, so it is convenient in some sense. Now, what happens is that in extended supergravities, typically supersymmetry couples some of the scalar fields. Couples means combine, transforms, connects some of the scalar fields to the P forms, to the P form fields. This means that if supersymmetry is large enough, and this is the case for extended supergravities, scalar fields and P forms lie in the same supermultiplet. They are connected to one another by supersymmetry. For instance, in 4 dimensions, there are scalars which live in the vector multiplet, okay, which are connected to vector fields by supersymmetry, acting on them by supersymmetry. Okay. In in n equal 1, so in a minimal supergravity in 4 dimensions that is not extended, number of supercharges is 4 in that case. This is not the case in 4 dimensions because we have chiral scales within chiral multiplets, and they are connected only to sigma multiplets, but not to P forms. Okay, in this case, what happens is that supersymmetry fixes the couplings of the scalar fields to these P forms. Fixes the couplings of the scalar fields to these P forms through the kinetic term of these P forms here. Okay, I will show you now how this is done. So these couplings are fixed up to a residual freedom. Let us now write down for a P form like this the kinetic term. Okay. Let us now write down the kinetic term for a P form, the generic form. In the case in which D is different from 2D plus 1. So we first focus on this case because it's the simplest. Okay? Then we will consider also the case in which D is equal to 2 times D plus 1. And there's equation, the form of the kinetic terms is more complicated. Okay, so what is the form of the kinetic term for these forms here? We can write it like this. the square root of the determinant of the matrix, absolute value of the determinant of the matrix, divided by 2k factorial, where k for me is p plus 1. Okay? Times an epsilon, which is minus k minus 1, which is minus 1 to the p, times a matrix, depending on the scalar fields, times f m mu 1 mu k, f m mu 1 mu k. Okay? This is the form, the expression of the kinetic term of a B form. Such that this is true. Okay? That's this simple expression. Notice that in the kinetic term depends on the scalar fields. The scalar fields enter the kinetic term. This is a general feature of supergravity. This is a general feature. And the scalar fields which enter here are those which are connected to the P forms by supersymmetry. And supersymmetry fixes this coupling, namely, supersymmetry fixes this matrix here. Up to some residual freedom in the choice of basis, okay? A redefinition of the field, linear redefinition of the field. But up to this, supersymmetry fixes this matrix, which defines the coupling of the scalar fields to the P form. Okay, this is an important feature. Now, let's write down the definition of this Fm. Fm is equal to D, which is a K form, is dCd. Okay. So the Bianchi identity is simply dFm equals 0. Okay, that's very simple. Because d squared equals 0. Okay, now let us write the equation of motion for these fields. To write the equation of motion is useful to define a dual field strength. Let's define it here. Gm1 mu d minus k is equal to epsilon times epsilon mu1 mu d minus k mu1 mu k delta L over delta F m mu1 mu k. Basically is epsilon tensor, which I always define as epsilon mu k. Basically is epsilon tensor, which I always define as epsilon 0, 1, d minus 1 over 1. Okay, that's the usual definition. That's the variation of L with respect to F.
So is your epsilon tensor density or is it?
Is it just yeah? So if you
Measure
want,
the square root of G in front or?
it's inside here.
Oh,
The square root of G is inside here. So it comes from N. Okay.
so it's not like, that's because I'm a bit confused. Are we always in Einstein frame or?
We are always in Einstein.
Okay, so no.
Always. No. So when we perform the compactification of dimensional reduction, we rescale the matrix, so we write the general form of the higher dimensional matrix, so that the lower dimensional one is in the Einstein frame.
Okay, so the dilaton is just one of the scalars. And
The dilaton is just one of the scalars.
It doesn't have a special role.
That's right. No, that's not. It's one of the scalars. And but you can identify it clearly. Very
It has
precise way.
specific couplings.
Sure. Choosing the parameterization of the scalar manifold, as we shall see, in a suitable way, you can identify, you can pinpoint all the higher dimensional, you can make manifest higher dimensional origin of all the scalars. Okay, so this is the definition of this GM, and you can verify that Gm, do the variation of this guy, that Gm is nothing but, as a d minus k form, this is a d minus k form, is nothing but minus mn phi star of f n. Okay. Now I'm going to define the star operator. Okay. The star operator is the so-called Hodge operator. It is defined in this way: star of omega mu 1 mu p, or it's mu 1 mu l, okay, l. This is equal to square root of g epsilon mu 1 mu l mu 1 mu d minus l omega mu 1 mu d minus l divided by d minus l factorial. This is the definition of the Hodge dual operator. This is the definition of the Hodge dual operator. So you see, it maps an L form into a D minus L form, or better, a D minus L form into an L form. So it will map a K form into a K form. Okay? Now, how do you write the field equations? The field equation for a D form field. Well, you can easily verify because G already contains the variation of L with respect to F. Sorry.
So we started off with a Colombian sector, which is people, right?
Yes. So far not. So far we have a formulation of our engaged superiority containing a number of p-forms. Now I will show you that how p-forms are dualized. So how you relate, you can construct out of a formulation an equivalent one by using this Hodge duality. Now I'm just focusing on one p-form and its description. Description in terms of Yankee identities and field equations. You easily verify that the field equations, so when the Yankee identities are dfk and equals 0, the field equations are g minus k and equals 0. Notice that here this index is up, and here the index labeling the corresponding forms is down. This will be related to a specific transformation property with respect to the global symmetry. Okay, so the position has meaning, contravariant versus covariant with respect to a suitable group, which we are going now to find. So these are the Bianchi identities and the field equations. You can identify the field equations at this form. Okay. Now we can dualize the P forms Cp into dual C tilde D minus P minus 2 forms. How? Simply by writing Gm D minus K, which is D minus P minus 1. Remember how K is defined, okay? As D of Cn. D minus okay, tilde. By writing these, okay, as D of this other object, okay. So, while in our original theory, the fields which are locally described in the Lagrangian, that is the elementary fields, are CP, we can define an equivalent version of the theory in which the elementary fields are C tilde. How do you do that? Well, it's a kind of like a Legendre transformation. It's a kind of Legendre transformation which you add to the Lagrangian. It's a kind of Legendre transformation which you add to the Lagrangian a coupling like this, L, a coupling like this, L, you add to it coupling like this, F, M, wedge, G, M, minus C tilde. Okay? You add a coupling like this, okay? Then you externalize equals 0, and this implies another, well, this gives you another Lagrangian which contains now only G. This is the way in which you dualize. This is a kind of Legendre transform that you do. The new Lagrangian will describe C tilde together with all the other fields instead of C. The elementary fields of this new Lagrangian are C tilde. This is equivalent because these two are equivalent ways of describing the same degrees of freedom. So they are just equivalent formulations. But you're trading Fm for Gn. Now, what you're doing is you see the new formulation in the new Lagrangian, the new theory, which is the dual theory. Now, dGn equals 0 are the Bianchi identities. The same now are the Bianchi identities because G and are D of C tilde. And D F M equals 0 are now the field equations. So what you're doing by dualizing, okay, you're exchanging both Bianchi identities and field equations. Now, it turns out that I will show you why equivalent formulations of an engaged supergravity, of a same engaged supergravity obtained in this way, differ in general in their global symmetry group. The global symmetry group will be different, or maybe different in general. Okay? So if I do this, what changes is the global symmetry group of the theory, meaning of the field equations at the end. The reason for this is that, as we shall see, the global symmetry group of an ungauged supergravity is related to the geometry of the scalar sector. More specifically, it is determined by the isometry group of the scalar manifold. The scalar fields are described, as we shall now in a moment, by a nonlinear sigma model. The global symmetry group is the isometry group of this nonlinear sigma model. So the symmetry group of this nonlinear sigma model. If we dualize forms, okay, in this way, in general, this will change the number of scalar fields and change the geometry of the scalar sectors. For instance, if we are in 4 dimensions and we have 2 forms in 4 dimensions, okay, we can choose to dualize the 2 forms into scalar fields. In this way, we are increasing the number of scalar fields, and also the structure of the scalar manifold will be different. And also the global symmetry, the isometry group of the scalar manifold. Okay? Yes. Yes, I will. Now I'm going to show why.
Because you get two currents from one is
Uh-huh.
and another one for the other game.
But that, okay. E77, I'm talking about the global symmetry group. So the global symmetry group is E77 in the maximal supergravity. Yeah. In the case of, but in a specific version of maximal supergravity. For instance, if you compactify 11-dimensional supergravity on a torus, okay, you end up with on a torus down to 4 dimensions. Okay, here does not have an E77 symmetry. But what you can do is you dualize the two forms or all forms to lower rank forms. Okay, in doing this, of course, you will in general be increasing the number of scalar fields. In the version in which you dualize all forms to lower rank forms, okay, and therefore the scalar sector is maximum, okay, you have the maximum amount of global symmetry. You have the maximal isometry, because the scalar manifold is maximum in that case. And in that case, you have E77 in 4 dimensions, E66 in 5 dimensions, and so on. So only when you dualize all forms to lower rank forms, then you have these exceptional groups in the maximum. Okay, what you mean by symmetry associated with the vector fields, you know? Well, these are the locals. These are the locals. The locals, the gauge symmetries, which are trivial in the ungauged case because nothing is charged. This in the ungauged case is always U1 to the number of vector fields, and nothing is charged with respect to them. They're always there. Okay, good. So let us see how global symmetry acts on these. By the way, this relationship between duality symmetry G, right, G, and these duality covariant, these duality related formulations of gauge supergravity was discussed in paper originated in a paper by Kremer, Julia, Blue, and Pope called the dualization of dualities. So this dependence of G of the global symmetry group on whether we describe the same degrees of freedom in terms of C or C theta, that is called the dualization of dualities. Okay? So how do global symmetries act on okay, let's use this on P forms. Let's use this expression of the kinetic term for the P form. You see that if we transform Fm with a linearly by a constant matrix, which I call S, let's call it S minus 1, M, Fn, I transform it like this. And if I transform M and N as this, in this way, you see, if I transform F, the field strength, in this way, and the matrix M in this way, you see that the kinetic term is left unchanged because all these S matrices they just cancel. Indices are contracted in an invariant way so that they will cancel out. Okay. So global symmetries on P forms they just act linearly as a transformation of this kind. However, here there is a sample. What's up? Well, M is not an independent field. M depends on the scalar fields. Okay? So, in order for this to be a symmetry, it has to follow from a corresponding variation of the scalar fields. This has to be equal to M and N of a simple y prime. Clear, because symmetry means that the equation of motion and the angular derivatives have to be invariant in form, okay? And therefore M, okay? Okay. So, a global symmetry transformation of, so a linear transformation on the B form, it must be combined with a transformation on the scalar fields. Necessary. This is related to the fact that these P forms couple the scalar fields because of supersymmetry. So there is supersymmetry behind every step of these derivations. Okay. Okay. So let's describe scalar fields. How are scalar fields described? Well, let us write the most general kinetic term for the scalar field that we can write. Let us write the kinetic term. We have d mu phi s d mu phi r, where s and r run from 1 to and s number of scalar fields. Okay, then we have 1/2 here. Remember, we are in mostly minus. And here we have two free indices. Okay, so I can still contract this by a matrix GRS, which is itself functional scale. Okay, so I can still contract this by a matrix GRS, which is itself functional scalar fields. Now, scalar fields, they can occur nonlinear reaction because they don't carry space-time indices. Okay, so this matrix can be a linear, nonlinear, and in general, it's a nonlinear function of the field. This is the most general thing we can think of. Okay, of course, there has to be a square root. Okay, this is the more general expression we can work out, or the kinetic term of the scalar. But the positivity condition on the kinetic term, the condition that there should be no ghosts, implies that G Rs in this function here has to be positive. Now, this is the Lagrangian of a nonlinear sigma model. Nonlinear sigma model, in which, you see, we can consider the scalar fields as coordinate on a manifold, the scalar manifold. Riemannian. Which is also going to be simply connected. Okay? Riemannian manifold. Riemannian Y, of which G with matrix G Rs of phi. It is Riemannian because this matrix is definite, it's positive. Okay? So we have two manifolds, one on top of the other. Space-time manifold in d dimensions, and we have an internal manifold spanned by the values of the scalar fields. Let's call this manifold M scalar. Okay? So for each x mu, the scalar field defines a point in the scalar manifold. So this is a geometric picture that it's very useful to keep in mind when studying supergravity. There are two manifolds. One is the external manifold, d-dimensional spacetime, and the other one is an internal manifold, the scalar manifold, of which scalar fields are coordinates. Okay. Now, we have seen that in order for this transformation, for a linear transformation on the C form to be, of the P form to be a symmetry, it has to be combined with a corresponding transformation on the scalar field. How much time do we have?
Whenever it's a good time to take a break, we can. We're about 1 hour.
Okay. I just finished one derivation. So this transformation S should correspond to a transformation on the scalar fields. Okay. Now, in order for this to be a global symmetry of the theory, this transformation on the scalar fields must be the scalar action in back. Now, the scalar action is nothing but the line element on the scalar element. So symmetries of the scalar action are nothing but isometries of the scalar element. Namely, this S should correspond to a transformation, which in general is nonlinear transformation on the scalar field, which is an isometry of the scalar element, that is of the matrix of the scalar element. Isometry, I mean that G R prime S prime of D, function of phi prime of phi. I suppress here the indices of the scalars. D phi prime R prime over D phi R, D phi prime S prime over D phi S is isometry of the scalar element. And you can easily verify that if I make a transformation like this, which in general is a non-linear transformation on the scalar fields, okay, with this property here, namely an isometry, the action is clearly valid. You can easily verify this. The action is clearly valid. Okay? Because the derivatives will change precisely by this Jacobian. Okay? And you easily see that the action is valid. Okay? So S should correspond to isometries. This is a necessary condition for a linear transformation on the P forms to be a global symmetry of the theory. It implies a transformation on the scalar fields. The transformation on the scalar fields is a symmetry provided it is an isometry. Is this true also? Is it also true the reverse? I mean, does any isometry correspond to a linear transformation of this kind on the fields? I will answer after the break. Okay? Now we can have a small break.
All right, thanks, Mark. Yeah, we're going to have a 25 minutes of break.
And that guarantees that
having trouble with Jerome. Do you know what the credentials should be? But, I'm using my best credentials and it's kicking me out.
Really?
Yeah,
Try to put the in.
I did. And select version still refused. Resulted to using type.
That's good.
Yeah, but now and again I need to reload it.
I'm sure was that also the same problem. Because I thought that was the whole point of it.
So did I, but maybe it will also change. Yeah. coffee.
What?
Not just, on the coffee breaks, you do coffee, but you don't do the coffee breaks.
No, it's, because you was using my phone, because I'm catching up on.
Oh, I
That's
see.
like a backlog of emails and texts.
I see. You know what that goes on? Secretary. Yeah. Uh, 5 minutes, and if you get this statement, those are nice hours. You might should be honest. Yeah. And it took away my certificate, you know, I spoke. So I haven't got my MSc certificate.
Oh, yes, you know, the admin.
We tried. It's a big university building.
No, 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 it's like Titanic one, that's the corner.
Yeah.
That looks like the,
Oh,
the road is there. I can show you tomorrow.
no, I know what it is. It's just trying to build a wall.
Actually, when you were having lunch, when I walked right by, on the lunch place,
Yeah.
there's a nice walk where you literally, it's actually crazy how close it is from that point.
Is it?
It doesn't like, you don't see the sun. Because like, you know, one of the nights like
Well, I didn't walk from that place. I once part of the main entrance on the other side.
the main unlimited.
Yeah.
Okay.
And walk all the way in, and that's why I'm familiar with that place.
Okay.
It's just like I didn't know the walk.
Yeah.
Yeah.
Well, walking from main gate all the way here, when you're in the rush, it seems you are not covering enough distance.
Yeah.
It's just like there's more space, it's like the space is stretching us.
Exactly.
But we're taking casual,
Yeah.
but it's really, like, I was actually impressed with the long video. Good afternoon.
Yeah.
The sun goes down.
I see. No, I think one.
Yeah.
Oh, Friday. We'll see. I can just you next week.
I would recommend Thursday, Friday, everybody's on bottle food.
Oh, I see. That is
That's
true.
why I was
Yeah. And you get a price to that, say.
oh, yeah, okay.
Yeah.
Especially since, yes, the dedicated 1 week now.
Yeah, the students finish exams, you know.
Yeah.
Oh, okay.
A lot of them, like this morning,
You know,
it was like, when I was coming in, they taking it back.
there's quite a lot more students that are in university, so I assume that it's probably still in exams.
Yeah, the exam season is not officially over, but for the remotes, it's actually, now we probably exams
You know,
and the dates just don't want to go high.
you guys don't have to overwhelm.
Like, what is the whole, looks like today,
Why are you saying that? What's the day today? Some people are getting paid today, so it's a good day for some.
so for me, the big thing is that it's not raining, so
Oh, okay, there's no cost.
we don't have a lot.
That's odd.
That's what we're running.
Yeah, but I would assume that there will be quite a few locals on campus. Is it?
Yeah, let's say, I
Swimming pool.
exactly.
But, so I assume
They
they
were
were trying.
attracting sponsors. The basketball. It's on.
Yeah.
There is one of the good basketball.
I see, but, yeah, also from the one, you know, for it. This is what it matters, so.
But what about how you?
How it goes, is how you. And there's the one with campus, 3 quarters on the west. There might be one close to the river.
I think they have 4.
Uh,
And first, or team and 2.
The indoor is quite huge. There's visit to about 4 people. That's quite
It's
massive.
a really,
Yeah.
that's. Unfortunately, looking door, but then you have to jump through all kinds of, because the gymnasts are competing in space.
Yeah.
What do you call it? Tennis looking thing?
Badminton.
Badminton, they also compete in space. Down south. And those guys have a lot more momentum.
Why? What I would assume that they'll be interested. No.
At high school level, it's,
Yeah.
organized in its own facility.
Yeah.
So that's
Surprising.
and that's one that, attractive on that's one of the,
No, when football attracts the wrong crowd.
this is the best way.
No, things have changed. When I was young, I used to play basketball. It was mostly, the prim and proper boys who try to do everything. Whereas football was the opposite. Exactly. So, things have changed.
I think there was an excitement around
Yeah.
on the substance because we had
That's popular everywhere.
how do you play it? I'm like asking for me, and that's what I'm thinking.
What's his name? That's why they were arrogantly there to proclaim that they use this stuff. Kevin Durant.
I can't do it.
Yeah. I suppose you build tolerance. Because I know at some point the government was also mentioned smoking occasionally. There's
But my son,
I don't know whether before a match, I don't know, but I know Kevin Durant was a interview he did with what's his name, David Lamb.
okay,
And I said on the show that at that moment,
he was under.
yeah, I like him.
I like his game.
Yeah, I think also like him as a person. But I don't know much of him as a person.
Yeah.
But the way he carries himself,
I'm not sure where,
yeah. I think he has a kind of advantage, but that's in these days. You see, I think they're thinking about guns or something. Yeah, especially when you put it like that. It's cool to see smoking that. Whereas in my day, we were considered a protest. Whereas now it's country. What's his name? The guy with the podcast. Even Elon Musk has smoked that stuff in public. I mean, you're very much my type of business. I could be it. When you go to restaurant, you know what the interest is. If you go there around that time, quite a lot of students are smoking. It's normal.
but where did they get it?
You can make 5 to 9. Like if not get like what's this? Uber food. You can actually, there's an app called Uber Zone. It's an app. It's a website. So you can order online and you can. It's becoming mainstream.
deciding to get it for, actually,
I'm open-minded about it. It's just, yeah, it's just. Okay, well, I'm not talking about the lands, but I'm talking about the, it's all of the access, the stream.
and so that, there was one guy in the class.
Yeah.
Like, he says, he had the reflexes on. He had reflexes on custom.
It's just slow. It's like, I've never heard a story where somebody had been like people smoking that stuff and then went about the park and or something. Yes, and it's slower, very slow. But yeah, in terms of impact on other people. I'm saying oh, okay. Because you would think that the most stories like sometimes to be used in the same ages. I'm sure there's something.
I'm not well versed.
Yes, it's okay. So,
I suppose. Oh, right. I mean, I was thinking a lot. That's just.
Right,
actually,
okay, so let's continue with the last lecture of today.
okay. So let us resume from where we stopped. We showed that a linear transformation on the CP forms, so the P forms, okay, has to correspond to a isometric transformation on the scalar manifold. The reverse is also true, because what happens is that supersymmetry implies that on the scalar manifold, structures are defined to be P forms. Okay, so the fact that the scalar vector P form belong to the same supermultiplet reflects or implies that on the scalar manifold, okay, structures are defined. Structures are called fiber bundles. Okay, and these structures fix up to certain residual freedom, fix the coupling of the scalar fields to the P form. Let us be more precise. I will not go into the detail of these structures, because then I will focus on homogeneous manifolds, and I will show how for homogeneous manifolds this coupling are defined in terms of the cosette representative, okay, which is quite straightforward. So, on M scalar, okay, structures called fiber bundles are defined, implied by supersymmetry. I will not enter the detail, the mathematical detail of the general definition of these bundles, but only I will list the implications of these structures. There exists a representation RP, let me call it RP, representation of G equal isometry of the scalar manifold, such that for each G in G, there corresponds to RP a matrix RPG, which is an NP times NP matrix. Okay? Homomorphism. And this is a representation to on the scalar manifold, the matrix Mn as a function of the point of the scalar manifold is defined such that for any G in G, which maps phi into phi prime, function of phi, Mn phi prime equals Rp of G, MP Rp of G, NP M Mn phi. Now you see that this structure defined on the scalar manifold guarantees that the matrix M transforms at each root, so that the kinetic term of the P form is in fact invariant. So we find that invariance for the kinetic term of the P form which is defined by whose group is the isometry group of the scalar manifold. Phi goes into a phi prime, function of phi, in general nonlinear. F M K go into an F prime M K, which is R P G M minus 1 and P F K. And M and phi goes into M and phi prime, which is RP of G, M P RP of G, and Q M P Q of phi. Okay, you see this combined action is an invariance now of the kinetic terms of the scalar fields, isometry group, and of the P form. So there is a structure which is called a bundle structure, in which the P form or their field strength transform as sections. Namely, they have a well-defined transformation property. This one. we are on a point in the scalar manifold, and we go from one point to another point through an isometry, then what happens is that Fk goes into Rg, or the F prime, okay, which is given by this matrix. Okay? Yes.
Is it possible then to replace the fiber particles with sheaves, not sections?
Sheaves in what sense?
As in covering your scalar manifold with the compaction in
Yes.
sheaves.
Oh, you mean if I can cover the whole thing?
Yeah.
Yes. You can cover the whole scalar manifold. Because in the manifolds we are considering, the action of G is transitive. So you can reach from any point, any other point. This is indeed this is true for supergravities, which are n greater than 2 in 4 dimensions. Okay, and in 5 dimensions. Then this is guaranteed. N equal to 2 theories in 4 dimensions. In these cases, the scalar manifold can be non-homogeneous. In that case, you cannot cover the whole manifold. But we shall focus on homogeneous manifold because otherwise the treatment of non-homogeneous manifolds requires the proper formulation of this fiber bundle and special geometry, special Taylor geometry.
Is there a special reason that cases, very mostly cases of special?
Because
There's also for any one.
also for an equal one, yeah. But here we are focusing on maximum, on extended supersymmetries. Well, the reason is that when supersymmetry is large enough, also the geometry of the scalar manifold is more constrained. Okay, so when n is greater than 2, the symmetry, well, the scalar manifold is not just homogeneous but also symmetric. For n equal to 2, supersymmetry is not strong enough to guarantee the homogeneity, and you can have manifolds with the structure that you need, but which are not homogeneous. So they are not closed spaces. So in that case, you really need the formal definition of fiber bundle. Okay. In all these cases, 4-dimensional cases, okay, you have on the scalar manifold a flat symplectic structure, which defines this action for manifolds. Okay, but in that case, there is a complication because there is electric magnetic duality. I'm coming to that now.
So are you really having the hours? Are you really also having the hours for non-homogeneous?
Yeah. These also include two manifolds that arise from Calabi-Yau manifolds, Calabi-Yau complications.
Unfortunately, these are not.
Which are not homogeneous in general. Well, classically, you can find manifolds which are homogeneous, okay, at the classical level. I'm not talking about the Calabi-Yau here, I'm talking about modular space, the classical modular space. So, scalar manifolds, the modular space. In that case, you can find, but then you have to consider also quantum corrections and all that, and then this may spoil, and will in general spoil homogeneity. You're talking about modular spaces. Okay, so this is basically the general structure, okay? The general way in which dualities work, okay? Now let me consider theories which are or versions of these are dualized into lower order forms. Okay? So in these formulations, which is equivalent, of course, in these formulations, the scalar manifold is maximum and so also the isometry group of the scalar manifold, and therefore the global symmetry group is maximal. Because now I want to discuss how this global symmetry group acts on all other forms, okay, including those forms whose dual have the same rank. And here there is a subtlety, because there is an issue of electric-magnetic duality, which was not there. Okay, so let us restrict to the version of H superiorities, which all forms are dualized in terms of lower order. Okay, so in the case of maximal sugar obtained from D equal 11 of 11 dimension super on Tn, so n-dimensional manifold, in this case n is equal to 11 minus d. Then, in the version in which the scalar manifold is maximal, all forms are dualized into lower order forms. G, the global symmetry of the theory, is an exceptional group at the classical level of this form. This is the maximally non-compact version of the exceptional group E11 minus D. In 4 dimensions, you have E77. 6 dimensions, you have E66. In 5 dimensions, you have E55. And E55 is not an exceptional group, it's SO55. In 7 dimensions, you have SL E44, which is SL5. It's not an exceptional group. So you have truly exceptional groups only in 5 dimensions, 4 dimensions, and 3 dimensions. In 3 dimensions, you have E8. It's the exceptional group. In dimensions lower than 3, the exceptional group becomes an affine Casimir element, okay, in infinitely dimensional, okay. So in that case, the situation is more. Okay, so let us now focus on this kind of supergravities. These versions of supergravities, engaged supergravities, in which now there are p forms such that d equals to 2, d plus 1. This was the case that we excluded. Now let us consider this case. Example, 4 dimensions and vector sequence. Okay. So how are these? How do these forms occur in the Lagrangian of the engaged theory? Okay. How are they described? And how does the global symmetry group act? As we shall see, on the scalar manifold, the part of the scalar manifold is having the scalars coupled to these forms. Okay. There is a structure, a fiber bundle, which associates with each element of the isometry group a transformation acting, transformation that is a representation, okay, acting not just on the K form field strengths, but also on their magnetic fields. Okay. So let us consider this case. Now you see, once we have dualized all forms to lower order forms, okay, the formulation of supergravity is not unique. We have different formulations of the same supergravity theory. Why? Because we have CK forms, CP forms, okay, which can be dualized to dual forms, which are again CP forms. Okay. Now this will not alter G, the global symmetry group of the field equations and the angular will not alter our symmetry group because the scalar sector is always the same. Okay. However, what changes here is the Lagrangian. Here we're going to have a Lagrangian in which the P forms are described as fundamental fields, and here we're going to have a Lagrangian in which the P tilde forms are described as fundamental. Now these two Lagrangians are not equivalent in the sense they are not related by local theory definition. So we have inequivalent off-shell descriptions. Depending on which of the two p-forms, we choose to describe in the Lagrange, either we choose p or p tilde. We're going to have different off-shell descriptions. In particular, these two Lagranges will differ in their global symmetry group. In the presence of this p-form, G, the global symmetry group, is not going to be a symmetry group of the Lagrange, because it will act on both field strength. Field strengths, and therefore it will have a electric magnetic duality action. It's not like in this case. In this case, G was a symmetry of the action, of the p-form action. In this case, in the presence of these p-forms for which k is equal to 2, p plus 1, G will act on and will mix the field strengths and their Hodge-Duals. Okay? So it will not be in general symmetry of the Lagrange. It will be a symmetry, global symmetry, of the field equations and the identities. So G will be an on-shell symmetry. Off-shell symmetries will be smaller, will be the symmetries of the Lagrange. And they will depend on whether we choose to describe as an elementary field C or C tilde. In these cases, we will have two different off-shell symmetry, global symmetry groups. If we choose L or G prime E contained in G, we choose L prime. Okay? And when we're going to choose the gauge group, then we'll have two possible choices here. Because the gauge group can be chosen only within the global symmetry group over Lagrange. Because it's going to be a symmetry, a local symmetry of the Lagrange. So the gauge group has to be chosen within the global symmetry group of the Lagrange. According to the off-shell description you choose, you have different choices for the gauge group. Because you have different global symmetry groups of the Lagrange.
And this is when we decide to gauge. This is when we decide to gauge.
This is when we decide to gauge.
Because for now, the gauge group is just...
For now, the gauge group is just U1 to the end. But then for the gauging, this is going to be relevant. Because for the gauging, you have to choose a global symmetry group of the Lagrange with certain particular properties, and then promote it to local symmetry. And then follow a certain procedure, well-defined procedure, that will guarantee that the final theory will have the same amount of supersymmetry as the region. Okay, let's give the general structure of the Lagrangian, the kinetic terms for these special p-forms. Here it is. So, the Lagrangian for the p-forms, where d equals 2p plus 1, have this result. So it is a square root of g. Okay. Then we have a minus here. And then we have to over 2k factorial. Again, k is equal to p plus 1. I lambda sigma of I f lambda u1 k f sigma u1 k, okay, plus r lambda sigma phi f lambda u1 k star f sigma. So you see, the first term is just the same as the one describing the generic P forms that we wrote before. But now there is another term that you can write, and this term is there, and is implied by supersymmetry. So you have two terms. This term is independent of the matrix because the star contains 1 over G, which transfers here. Okay? So this term is independent of the matrix. This term is dependent of the matrix. Okay? So for vector fields, equal 4, equal 1, this structure generalizes the F mu nu, F mu nu, plus theta F mu star F mu. This structure generalizes this general form, okay, well, generalizes the net term of the vector fields and the theta term. Okay. In particular, this matrix R lambda sigma generalizes the theta term. This I generalizes the capital. Okay. Now, I lambda sigma has to be symmetric. But R, you see from here, is anti-symmetric. Sorry, it depends. It depends on it depends on K. It's minus epsilon R sigma lambda. So its symmetry depends on epsilon. You can verify this from here. You write explicitly the star, and you verify that R has just a particular symmetry property. Okay? This you can check.
But don't you think this is the same as F by F, right, or something?
This is F by F. Let's write it in an equivalent way.
So
So if I write the LP as a G form, this can be written easily as minus 1 over 2 I lambda sigma F lambda wedge star F sigma, and then plus epsilon R lambda sigma F lambda wedge F sigma. Okay, you can check this also. That these two things are equal. Okay.
So that will be, yeah, that's obvious why you are.
That this is obvious. Yeah. Okay. Now we can.
Sorry, may I ask you, for the usual complement beta term, of course, we know that they combine into a complexified
Yes.
version. And is there something?
It is.
You're going to say yes?
I'm going to say that. Yeah. So, in fact, in this case, there is an interesting duality structure. Okay. So let us define now the dual field strength. So what we define as G there. Let us define the corresponding dual field strength in this case. As G there. Let us define the corresponding dual field strength in this case. And then I'm going to give you some exercises. So, G, lambda, E1, mu K, still a K form. The dual field strength is still a K form. This is defined as epsilon mu 1 mu K, mu 1 mu K, delta L over delta F lambda mu 1 mu K. Okay? And what is this? I need you to check. You do the variation of this Lagrangian, okay? You contract the epsilon. And what you end up with is I lambda sigma times star F sigma mu1 mu k plus minus epsilon r lambda sigma F sigma mu1 mu k. Okay? You can verify this. Check. Check. In compact form, let us write this as a K form. This is equal to minus I lambda sigma star F minus epsilon R lambda sigma F sigma. Okay? Again, epsilon is equal to minus 2 to E. Okay? Minus 1 to E. Right? Okay.
For the variation person, we use that star F is dependent on.
Of course.
As well.
Yeah. You write explicitly star F and you vary. You vary.
You write star F as epsilon and F, and you vary that as well.
Precisely.
So that you get the same factor of 2 as in the case.
So you get the factor of 2 from each. Okay. So I suggest you to do explicitly perform explicitly this calculation. Okay. So you end up with the G lambda like this, and you compute you should use also this property. Okay, if you use this property here, it is useful to group the two strands in a single array of field strengths, whose upper part are the field strengths F lambda, okay, and lower part are G. So let us group these, the field strengths and their duals, in a single array: F lambda, mu1, mu k, and G lambda, mu1, mu k. Okay? Let us put that in a single array. The reason will be apparent now. So I define an FK, K4 with an index m. You see that the index m, now lambda runs from 1 to np, np. But m runs from 1 to 2 np, because they run. Okay? Now, why do we use this? Because the global symmetry group will act on this vector here and will mix F and G. So it will act as an electric magnetic dual, a generalized electric magnetic dual. It will combine electric fields with their magnetic fields. Okay? So it will be a generalization of the U1 duality symmetry of Maxwell's equations. Okay. Now, there's another computation which is very useful to do. Okay. You have computed here G in terms of star F and F. Now, from this, you derive star F in terms of F and G. Okay, star F in terms of F and G. And you also compute star G, okay, by acting on this star and using that star is equal to minus to the epsilon. Okay. So you can compute the star of this Fm here, of this array of field strengths, okay, and express them in terms of F and G. For instance, here, star f is already expressed in terms of f and g. You just need to invert this relation. Okay? You put this on the other side, bring this to the on the other side, and then you get, and so you get lambda I lambda sigma. This is the inverse of I, okay, times G sigma minus G sigma plus epsilon minus epsilon R sigma gamma F gamma. I wrote this on the first side, left hand side, G on the right hand side, and then I multiply both sides times this matrix, which is the inverse of G, of I. I lambda gamma, I gamma sigma is equal to delta lambda sigma. Okay? So you express in this way star f instead in terms of G and F. Similarly, by acting on this by means of a star, okay, you can express star G. You do this computation, and what you end up with is this. That this is equal to minus C epsilon times a matrix M times F. Okay? Where this is what you find, where the matrix M and C are now 2NP times 2NP matrices. Yeah. This one up? Okay. Okay, where C is equal to 0, 1, F 1, 0. And M is a special matrix, which is defined as M. Mn is equal to I minus epsilon R I minus 1 R, where the matrices R and I are defined here. Minus R I minus 1, epsilon I minus 1, R I minus 1. Okay? This is a 2NP times 2NP matrix. Okay?
Notation I somehow standard.
Huh?
Is the notation I somehow standard? Because it looks like identity matrix.
I'm sorry, no. Usually it's
Yeah,
it's referred to as calligraphic I, but so I is a matrix.
but why I is what is it?
Well, there is a reason. The reason is that it is the measuring path of a complex matrix, which for epsilon equal to -1, of a complex matrix, which is the generalization of the tau complexified structural constant. Okay, so the reason why this is called R and the other is the structural constant. Okay, so the reason why this is called R and the other is called I and the other is called R. Real and imaginary part for epsilon. Now I'm going to get it down. Okay, so we find let us write these matrices here.
Can I ask a question before you
Sure,
read that Lagrange there? I mean, is a statement that these kappa field strings cannot couple to lower dimensional ones, or we're just not including that part of the language? Let's say, can a 4-form field strength couple to F2, like, F4 times F2 times
In
F2.
general,
Wedge F2, wedge F2.
that's true, that's true. So in general, for P forms, you can have in the dimensions so-called Chern-Simons terms in the Lagrange. This can be, they do exist in dimensions greater than 4, for instance. In 5 dimensions, you do have Chern-Simons terms. Okay, in 5 dimensions, you don't have this.
But then, okay, remember, in 10D, at least we shift the F5, right, for the next 3D.
That's right, that's right. In that case, in 10 dimensions, you do have, you do have in that case F5. But in the case of F5, F5 is subdual. You don't have this structure. Because F5 is a singlet with respect to it's subdual. Basically, in that case, F and G coincide. Okay. So in general, this is the general form of the kinetic term.
So in general, we're ignoring Chern-Simons terms.
We are ignoring Chern-Simons terms. In 4 dimensions, there are no Chern-Simons terms of this form.
But we're not in 4 dimensions now.
And D dimensions, yeah.
So in principle, there would be another contribution to G.
That's right.
With
That's right.
even lower.
Definitely.
And will
But everything will. Here we are focusing only on the kinetic term, but in general, everything will be written in a form which is manifestly G-invariant. So also the Chern-Simons terms will depend on a tensor, which is a G-invariant tensor. Chern-Simons term does not depend on scalar fields. So the tensors defining the Chern-Simons term, since it does not depend on scalar fields, should be itself a G-invariant tensor. Okay, so in that case. But here we're just focusing on the kinetic term, okay? And so what are the field equations and Bianchi identities for this case? For this case, well, the Bianchi identities are the same as before. Bianchi are D, F, M. Okay, so D, F lambda equals 0. Okay? The field equations are D, G lambda equals 0. Same as before. Okay? But this can be written as a single equation. The Fm equals 0. Okay? So it seems that everything is encoded in this very simple equation. Very compact one. And you see whatever linear transformation I do on Fm, that's a symmetry. However, we should be reminded that Fg is not independent. G is not independent. G is a function. See, the way we defined it, G is a function of F and of the scalar fields. Of F and of the scalar fields. G is a function of F and of the scalar fields through I. Recall that I lambda sigma is a negative definite matrix. Okay? Just like the matrix M for the generic default. And this is the positivity domain for the kinetic term of the default. That requires I to be less than 0 in order for there not to be ghosts propagating. Okay? So we have to remember that G is not independent. How do we take care of this? Well, through this equation here. This equation here tells us, in a somewhat covariant way, and we are going to see now covariant with respect to both, that G is not independent. So we have to combine this equation with this other equation, star F equals minus C epsilon M of phi times F. Okay? These two are the equations describing the P form in the case 2P plus 1 equals D. These are the equations. Okay? Now, what are the invariances of this equation? I can change Fm by a s minus 1, just as before. Fn, just as before, s constant. Okay. Now, suppose that m transforms, this m transforms just as before. So suppose that m transforms like suppose that m transforms as m prime equals s m prime mn equals s mp s n q m dq. Okay. And now suppose that this is phi. This is m mn of phi prime. Just as before. Okay? So suppose that there exists a transformation in phi such that m transforms in this way through a suitable constant matrix, and the f transforms in this way. Then you see that this is an invariance, a global invariance of these two equations. Provided S leaves C epsilon invariant. How do we prove this? Well, let's write this in matrix notation. M phi prime, M phi goes into M phi prime, which is S M phi S transpose. Okay? And F goes into F prime, which is equal to S minus 1 transpose times F. This can be written as F minus 1 transpose, because you see, we are contracting the index of F with the row index of S minus 1. So S minus 1 transpose. Well, this is the action of an S transformation on contrary vector. This is the action of an S transformation on covariant indices, which are the indices of M. Two covariant indices, lower indices. Okay? Now suppose also that S transpose C E epsilon, S is equal to C epsilon. That is, S leaves C epsilon invariant. This is also equal to S C epsilon S transpose. Okay? So suppose that besides this transformation property, which is the same transformation property we saw for generic P-false, S also leaves epsilon C epsilon invariant. This is required because we want this equation to be invariant. Okay? Let us show that the two equations are invariant. The first is simple because it's invariant under any global any constant transformation. The second one is not trivial. Star F prime is equal to S minus 1 transpose star F. Okay. Now, what is this? Well, let us use the equation for star F. So the untransformed here. This is S minus S minus 1 transpose C epsilon M phi F. Okay. This is minus S minus 1 transpose. Now I can use this equation here, this property here, that S leaves C epsilon invariant. Okay. And I can use, and I can deduce from this property the property that 1. So S transpose C epsilon. S is equal to C epsilon. This means that S minus 1 transpose C epsilon is equal to C epsilon S. I just multiply both sides times S minus 1 transpose from the left. Okay? And here we get this equation. Okay? Now we use this equation to rewrite this as minus C epsilon S and 5 times F. Okay? So we got that star F prime is equal to minus C epsilon S M of phi F. Okay? Now what we want to find is the same equation in the transformed fields because of invariant. So what we can do now is we multiply times S transpose and S minus 1 transpose. This is the identity. See, this is the identity. We haven't done anything. But this is M prime, M of phi prime, okay? And this is F prime. This is F prime. This is M of phi prime. So you see that both equations are invariant, provided we can associate with a transformation, appropriate transformation in phi, okay, a linear transformation S, under which N transforms in this way as a metric, okay, and F transforms in this way. Okay. As for M, the matrix M, you can verify that M is always symmetric. M is always symmetric. Moreover, M transpose C epsilon is equal to times M is equal to C epsilon. So M is a symmetric matrix, and it gives C epsilon value. Okay. So what does this mean? What does this property mean? Or in general, what does this property mean? What is C epsilon? Let's have a look at C epsilon. C epsilon is an invariant matrix. C epsilon is an invariant matrix. Is equal to 0, 1, minus 1, 0, if epsilon is equal to minus 1, and it is equal to 0, 1, 1, 0, if epsilon is equal to 1. So you see, in this case, S has to be in SP 2 and R, because a transformation which gives this matrix invariant is a simplex. So duality transformations, that is, global symmetry transformations, in this case, epsilon equal to minus 1, must be represented by simplex. For epsilon equal to 1, they are orthogonal transformations, pseudo-orthogonal transformations, O and E command T. Okay? An example of epsilon equal to minus 1 is D equal 4, P equal 1. Vector fields. The action of the global symmetry group on the vector fields, field strengths, and their magnetic duals is simplex. It's defined by a constant simplex matrix. Epsilon equal to plus 1. An example is D equals 6, P equal 2. And in this case, so in the first case is 2 and 1 are and in this case SP to and sorry n SO or better O n 2 comma n. Okay, pseudo orthogonal transformation. Can you read it? Okay. So we needed that to each transformation on the scalar fields, which is a global symmetry of the scalar sector, there corresponds a symplectic matrix in the first case, a pseudo-orthogonal matrix in the second case. Does this exist? Well, this is implied by structure, which is a suitable structure which is defined on the scalar manifold. Okay? On the scalar manifold, we have a structure defined, which is a bundle. In fact, it is a flat bundle on the scalar manifold, on n scalar, flat fiber bundle. In which the fiber transforms under the structure group is in one case symplectic group, in the other case pseudo-orthogonal group. Okay? Such that one, for any G in G equal isometry group of the scalar manifold, there exists, so there corresponds a Rp of G, which now belongs to SP2 and P are in one case O and P in the other case. So it is a 2 and P now times 2 and P matrix. As opposed to the case we considered at the beginning for generic P, for these special values of P, the action is doubled. And 2 m of phi prime, okay, is equal to R P of G times m of phi times R P of G transpose. So m transforms precisely that way. Okay. So on the scalar manifold, there is this structure which is implied by supersymmetry, which guarantees that there is a representation Rp of dimension 2 and P of the isometry group. Okay, such that the matrix M, which is a symmetric matrix, transforms in this way. M is either symplectic or pseudo-orthogonal, and this property is preserved by this transformation. Okay. So, and therefore, if we associate with each transformation, isometric transformation, which acts non-linearly on the scalar fields, a corresponding transformation on Fk R P of G minus 1 transpose R Fk. Then the action, not the action, the field equations and the identities, which I wrote before, are invalid. In general, in this case, the action is not invalid, as I said. The action is not invalid. Why? Because the effect of this transformation is to mix field strengths, whose corresponding to fields which are elementary fields of the theory, described locally in the Lagrangian, and transform them, combine them with their magnetic duals, whose which are field strengths or fields which are not described locally in the Lagrangian. Okay, so in general, it will act in this way. You see? Now, you immediately see from here that a generic transformation will not preserve the Lagrange. Will not leave the Lagrange invariant. Because the generic transformation, in order to be an invariant, okay, requires using the equations of motion. We see this from here. Let's consider prime, the transformed field strength under a generic transformation of this kind. This is equal to A times F. A is an anti-tensor matrix, plus B times G. Okay? Now, these are the field strengths of the transformed fields. Now, the Bianchi identity of the new fields, or the transformed fields here, whose field strengths are F prime, A and B are constant, they require the field equations of the original fields. The field equation of the original fields. Because if we compute df prime, this is A df plus B dg. Okay? Now you see that if B is equal to 0, then Bianchi identities of the original fields imply Bianchi identities of the transformed. The F prime, no need. Sorry. Equals 0, no need of field equations. Okay? But if B is different from 0, df prime equals 0, so the Bianchi identity of the transformed field requires the Bianchi identity of the original field plus their field equations. Okay? So this means that this is an invariance only of the field equations at Bianchi identities. Okay? Because the Bianchi identities of the transformed field require field equations. So it is an invariance provided you use the field equation of the original. So it's a non-Schoen's symmetry. But you see, now we can define those transformations, those for which B equals 0. So transformation for which B equals 0 is the symmetry of F. And they define the symmetry group, the global symmetry group of the Lagrange. Let me do this. So let us define GE inside the global symmetry group G. Let us define GE as the set of transformation in G for which Rp of G is equal to ACD 0. For which, well, this is -1 transpose, okay? Because the action, remember that the action then is R -1 transpose. So if R -1 transpose has this block equal to 0, then it is an offshell symmetry. It's a symmetry of the Lagrange. Now, clearly, this group depends on how G is embedded through RP inside SP2 and P or O and P. It depends. It depends on how this group is embedded in SP and O and P. Because if you change the embedding of G inside this, So this means that we are changing the basis of this representation. Clearly, the group which satisfies this condition changes. But if we change the embedding, we are changing we consider as elementary field to be described within the Lagrange. So we are making a choice of frame. Okay? What we consider electric and what we consider magnetic. And we are changing the Lagrangian description. G is always the same. What changes is the Lagrangian description, the offshore description, and of course its corresponding velocity. Okay? So, for instance, in equal 4, n equal 1, we have the vector fields under 4-dimensional theory. Okay? And this action is a electric magnetic symplectic action on the vector field strengths and their magnetic fields. What is the symmetry group of the Lagrangian depends on the so-called symplectic frame, namely what we call electric and what we call magnetic, on the basis of this symplectic representation. Okay? And so, depending on the symplectic frame, we have a different Lagrangian description with different global, off-shell global symmetry. The on-shell symmetry is the same. Okay? So this is the key point. Okay. What time?
It's a good point to stop.
Sure. Yeah.
Between 1 hour and 5 minutes.
Okay, fine. I will stop here then.
We'll leave the blackboard as is.
Okay.
Tomorrow morning.
So tomorrow morning after first. Okay. Okay. Thank you very much.
Okay, thanks a lot.
So if there are any questions, please do not hesitate to ask. Okay.
So this whole discussion is about the half dimension form refused.
Yes.
So you say
But not just 4 dimensions, but also.
but the half dimension, I mean the ones where the Hodge dual
yeah.
of the same dimension as
That's
the
right.
refused. So I guess for the other ones there's no.
There's no
ambiguity.
issue.
Yeah.
No. For instance, vector fields in 6 dimensions or 5 dimensions, there's no issue there.
Yeah, because assuming you've converted all the higher
Oh,
ones
to lower
you
ones.
already
Yeah,
said,
yeah.
So then the only remaining one is the half.
Is the half ones. And for that, you have this representation with double dimension. And now you see, I define this matrix M, which is a combination of I and R. Okay. Now, you were interested in this transformation property of tau, right? Yeah, and that's it.
Okay, so I guess that's, okay. But
Yeah.
if you're already answering, okay, because I'm thinking of how general reflections is there because vector fields are half
Yeah,
dimension,
precisely.
So,
Yeah.
equivalent now would be only for two form,
Yeah.
60,
Yeah.
two form fields, three form field strengths.
Precisely, only for this
Same
case.
structure.
But in this case, you see, you can define a matrix complex matrix, which is R lambda sigma plus I lambda sigma. And n prime is equal to C plus n times A plus n minus 1. So you see, this is very much like how prime is equal to C plus tau, let be A plus B. So let's say AB, CD in this case is in SP2. SP2. SSL2. In this case, it is in SP2 n, comma very similar.
So the value
This is, so this is SQLity of 4 dimensions.
Yes.
This is
This is a duality of 4 dimensions. This is 4 dimensions because it's okay. But you see, now I'm using this R and I matrices. 4 dimensions in general, these are non-trivial matrices, which are
If you have more than that.
of course.
No, but this structure is also for free-form field strengths.
Precisely.
Yes, so you are describing this.
Just the same. Yeah? Yeah, but in that case, you don't have an idea. Because in processing 6 dimensions, in 6 dimensions, you don't have an idea. Yet R plus I is not so. So in this case, it holds for epsilon equal to -1.
Yeah.
Okay. For epsilon equal to +1, and is equal to R plus I. Period. And then it transforms the same way. But you don't have the I is not very exact. So the thing, the case which is similar, also to the S duality of means, is this one, 4-dimensional case, because it's simpler. As the S duality is.
But this is not vector. This is not vector. These are still vectors.
These are vectors. These are open. Yeah, this is just vectors. Just vectors. And if you go to, so if you go to page, you look at four systems. Yes, in the 8 dimensions. In that, in 8 dimensions, you have 1. In 8 dimensions, you have 1 4-form and 1 empty, which are in a tablet, equally empty. You have an energy. And this is in a tablet of S. So which is S. So in your age, you have this inversion. Here you have the S.
Of course, these cannot be non-negative. These are well, the fun starts.
When you're yeah, but I wanted to compress everything now because I wanted to start.
But make contact with what
But no, tomorrow I want to write also this because
Let's see.